innovation and the global development initiative raised by President Xi Jinping. The world is confronted with changes of a magnitude unseen in a century, and things are picking pace. There are industrial revolutions and technological revolutions. There's never been such complex and interrelated developments going on at the same time. With societal development, scientists enjoy greater trust, and they enjoy greater support and are better placed in driving innovation technology into brings together various sectors, and transformation and upgrading happen more quickly. With the development of information and smart technologies, the global economic order and industrial development are reshaped. There are drastic changes to the way we live and we work. But then there were also challenges in public health, climate change, food security, and energy security, as well as environmental protection. There's a pressing need to provide greater, safer, and more economical and more effective solutions. The Chinese Academy of Sciences is the highest institution of our country in terms of the natural sciences. It's also the highest executive body in terms of science and technology. This year, we've had manned space mission to the moon, to Mars. We've also had various explorations on Earth. We've had this 500 aperture spherical radio telescope, the artificial sun, China's spallation neutron source. These are examples of our superior critical infrastructure in science and technology. We've also had various superconducting technology, nano catalysts, and also quantum prototypes. These are examples of our original research. We have achieved breakthroughs in critical technologies. These developments help facilitate our country's technological and socio-economic development. The CAS has been founded for more than 70 years. Our institution has formed partnerships with the scientific institutions, universities, and businesses from more than 130 countries across the globe. Overseas, we also have found the Alliance of International Science Organizations in the Belt and Road region, or ANSO. This means we are part of plans to nurture talent. And last year, we also set up an international research center on sustainable big data. Hong Kong is a vibrant and competitive place in terms of innovation. The SAR government attaches importance to science and technology as a way to drive Hong Kong's innovation and scientific development. The CAS also sets great store by collaborations with Hong Kong in terms of science and technology. Our institution works with Hong Kong's 6 universities in setting up 6 high-level joint laboratories. We set up Inno Hong Kong. There are also other forms of innovation. For example, in Hong Kong, the research outcomes are materialized with the support of the SCR government. Our institution also supports the work of the Association of Academicians in the GBA. President Xi Jinping, in his work report to the 20th Party Congress, said that we must regard science and technology as the primary productive force, talent as the primary resource, and innovation as the primary driver of growth. We need to make plans and establish a self-sufficient, well-established, highly productive, and open innovation and technological system so that we can lay a solid foundation that delivers results, and also we can have a resilient and sustainable system, providing the science and technological capability to provide support for the development and leadership and also longevity of our country. The CAS will work on 3 fronts. First, focusing on strengthening basic research. We will continue to play a role in helping our country with their scientific capacity. Basic research represents the basis and also the source of technological innovation. This is the solution to many technical issues. We need to deepen the work in the area. We need to identify the problems on the scientific frontiers, and we also have to come up with strategies and also take leadership where needed. We also need to bring different actors together to achieve synergistic effect. This is how we can provide technological support for societal development. Second, we need to expand international collaborations in science and technology to establish more open and efficient networks for collaboration. In COVID, there are drugs, there's COVID. We need to strengthen international collaboration on those fronts. We also need to step up our technological facilities and also innovative platforms. We need to work with partners on global problems to create new impetus for collaborations. The third front is that we need to step up nurturing young technological talent to unleash their creativity and leverage their vibrancy so that we can achieve the goal of turning our country into a place that brings together talent by 2035. We need to create more opportunities for young technological talent to create a better innovative platform so that young people can get focused on launching their own tech startups or working on their own areas. And that's how we can lay a solid foundation for future technological development. Looking ahead, let us work together and deliver greater results in major scientific areas and achieve greater breakthroughs in critical technologies. We need to deepen collaborations in various key areas of scientific collaboration and achieve a win-win outcome. Let us work together to drive scientific and technological advances and contribute to human well-being. Thank you.
Who shared with us just now. That leads us into the discussion session of our President's Forum. Now please join me and welcome on stage our moderator for this President's Forum, Professor Dennis Low, President of the Academy of Sciences of Hong Kong. Please welcome. Joining Professor Low, we will have his panelists. They are Professor Jin Guangting, President of the Hong Kong Polytechnic University. Please welcome. Next, we have Professor Rocky S. Tuan, President and Vice Chancellor, the Chinese University of Hong Kong. Please welcome. And we also have coming on stage Professor Alexander Wai, President and Vice Chancellor of the Hong Kong Baptist University. Welcome. And now, Professor Low, over to you.
Okay, thank you very much. So, my fellows panelists, so we have a chat for the next few minutes. So just now when I was listening to Professor Ono's talk, he talked about his university campus is building a next generation synchrotron. And that seems to me to be some sort of magnet for international talent. And then of course they have special brainstorming meeting built around that new facility. But when I'm thinking about Hong Kong, even though we have very good research outcome, deliverables, scientists, etc., but somehow I can't quite think about the existence of a national level research infrastructure in Hong Kong. For example, like many scientists, if they do world-class research, we have to go to Daya Bay or somewhere to do this. So do you think there is a need for us to build a national level research infrastructure? So maybe I'll ask Professor Tang first.
Thank you, Dennis. I think the answer is a definite yes. I actually spent 1 year as a VP for research at Sussex University, as you may know. And there, for example, actually it's not only major facilities or national lab. In national lab, of course, normally if we get one in Hong Kong, being designated as a national lab, that's quite good already. Annual investment is tens of billions, 10 billion, 20 billion, $30 billion. But recently I heard in Shenzhen they are setting up a quantum institute to be led by the president of Sussex. The rumor says it's going to be funded at 40 billion. So it's not only the major facilities or the space, and also the investment of money to hire researchers. When I was there, we had a Quantum Science and Engineering Research Institute founded by Shenzhen City, which was to grow to 900 people, I think, I remember. So basically in Hong Kong, we are very good at doing individual research. Sometimes curiosity-driven. When I first came to Hong Kong in 1994, the first grant I got from RGC was 0.8 million. When I stopped applying a few years ago, before I became president, it was still 0.8 million. So we are very good at giving a little bit of money to everybody. And they've done some research. Because we have really good researchers, world-class researchers. They have a good idea. They test it out, the idea in a small lab. And after that, they can no longer do very much. And this is one of the reasons why our research often stops at the academic publication stage. In some area, you don't need a big lab. In my own area, for example, we need a big lab. We cannot find it. I spent, from 2010, most of my experiments in civil structural engineering was done in Guangzhou. For a very simple example, maybe that is not a major facility, so to speak, for them. Their lab for structural engineering was 2,700 square meters. The lab at PolyU, we have a civil engineering, which is ranked among the top 20 in the world. The lab we have is 200 square meters, which is only 1/10 of what they have. So this is the issue of land and space that I would touch on later.
Thank you very much. Professor Tuan.
Thanks, Dennis, for that question. I'd like to point out that I actually agree with most of JG's points there. I think one of the things about a national lab, almost by definition, is a research infrastructure that allows national participation. That's a national lab. We can build whatever big-size lab we have in Hong Kong, but if nobody from the nation comes to this lab, then it's not a national lab. So how do you make that happen? So first of all, you have to first of all find a platform that has broad interest from various parts of the country. Hong Kong can be the leader or convener, if you want to call it. And then we have folks from different parts of the country come. Second important point is that it needs public-private partnership, namely the local government, the government from wherever that set of investigators come from, they also support it. If you have that, then you have a national focus, and you will be able to generate ideas, innovations, achievements that will benefit the nation. And so that's a national lab. One way to kind of think about it is to model ourselves after national labs that are very successful in various other nations. Europe has the EMBO labs, which basically serve that purpose. People can come from anywhere in the EU, they come in there and they train for 2 years, and then they return. And the United States, of course, also have national labs. Same idea. They have a set of facilities, the Argonne, Brookhaven National Labs, Lawrence Berkeley, Lawrence Livermore. People come from all over the country, managed by the local university, but under the auspices of a national initiative. So I think if we want to have a national lab, we must do those things and do it right and do it truly in a national level. Thank you.
Thank you very much. Alex?
Oh, thank you, Dennis. The good and bad things about speaking last is that all the good points have been made. Well, I agree, of course, with my colleague's view. But I want to add to the issue that I think the point is not to build a national lab or national laboratories in Hong Kong, but rather is have our scientists and engineers participate in national level projects. Because well, Hong Kong, well, we always think that we're very unique, we're very, very special, but we are actually a very small city. We only have 7 million. And when you use the word national, or let me turn around, big equipment, okay? Big equipment, these days, big science, big engineering, anything that really worthwhile doing an impact. We are talking about, scientists and engineers at the order of 1,000, okay, to devote to the effort or more. And so the real power to carry on a project like that actually has to come from a national level. And whether it happen to be physically in Hong Kong, that's what Rocky's point, okay? It's not that, that they have a synchrotron, they have, the light source, that we must have one, okay? But rather, we should participate, okay, in projects that really have impact. As JG said, most of the projects that, because the way funding are given, the way that our psyche is, it's an individual project, small team, a professor or two leading, 10, 20, research student, research staff, do a very good paper. And we always boast about how good we are in ranking in our research. But ask ourselves really, what have Hong Kong really contributed to? Now, of course, Dennis' work is world-class, really, application, of course. But how many of those work have we really done? I think that's something that is worth thinking about. Instead of thinking about, keep on thinking Hong Kong-centric. Okay, when you talk about science, big engineering, we should be nation-centric. Thank you.
Thank you very much. So I think all of that is very thought-provoking. So there are so many disciplines, but at least I suppose that with the help of Professor Sun Dong, maybe we should fight for at least maybe a small number of those national labs, and that encourage our scientists to participate in more national projects. Yes, please, JD.
Because when the central government actually were pushing for national labs, many provinces were trying, to build up their strength so that they will be able to compete and win a chance of building a national lab in their place. So I was involved in the Guangdong provincial lab for ocean science and engineering. They had 3 sites, one in Zhangjiang, one in Zhuhai, one in Guangzhou. So they invest money in this and try to build up the strength and compete, to try to win something. I think if we really want to do this, you want to have a national lab, which has to come from the recognition by the national system. We have to build a basis to show that we have that strength. I don't think it is fair for us to go to the central government and say, hey, we are one country, 2 systems. We are so special. Give us a national lab. I think we have to do the same groundwork.
Thank you. Now, another theme that we see in many of those videos is, of course, whatever cutting-edge work we do, ultimately, we need to be translated. So, and of course, I know that the 3 universities represented here have done a lot in the translation. So maybe Professor Tang, how has PolyU been developing that front recently?
PolyU has always been, from its very beginning, because PolyU was set up to support the industry, let me take this off, the industry in Hong Kong. So from the very beginning, we have a very close partnership with the industry. I think during many years in Hong Kong, PolyU's positioning, which is much more emphatic on application research, seemed a little out of place, in fact. Because in Hong Kong, when we had the GIF, it was for basic research. When we had AOE, it was for the basic research. When we had theme-based, it was for basic research. And when we went for money to the Innovation and Technology Fund, it normally is only for 2 years. So I think we had a difficult period, I think. Actually now, I felt that Hong Kong is moving in the direction that we would like to see. So I want to clarify the position of PolyU. Our motto is to learn and to apply for the benefit of mankind. So I always say in my university that you have to be doing world-leading research academically, but that's not enough. You have to move one more step further, to see whether your work has produced impact. When my colleagues come to see me about his, brilliance in research, I will only ask 2 questions. either whether you have changed something in your discipline academically, which will go down in your textbooks, or your work has changed the world, really. So one example I will quote is the DIMS technology for glasses. So if you have young children, you must buy a pair of these glasses if they have myopia, because this will slow down the myopia progression by 60%, and as a result, 90% of the current projected high myopia population, which is 1 billion, will become 100 million. Only 1/10 will be left. This is of a huge benefit to society in terms of saving medical costs, but also enhancing the quality of life. So this is one example where we did the work. They published, of course, but they also worked with the company to translate this into a product. And this guy is still a professor. This is one example to illustrate we always value this kind of translational work in addition to academic research.
Rocky, how about Chinese university?
Yeah, I think you were asking about innovation. Is that correct? I couldn't quite hear.
So what has CHK done recently to try to encourage, say, the development of a startup, the actual translation of our work?
Yeah. Well, maybe I'll still go back to innovation, because everything is built on innovation. And we often ask ourselves, and are also asked by others, what is innovation? And we have big projects that are called innovative something, innovation something. Innovation is actually the best definition I have ever heard about innovation is from a meeting that I attended, about 15 years ago, organized by the National Academy of Engineering in the US. Speaker got up and presented a slide. Unfortunately, I didn't have my phone ready to catch the slide, but I remember what was said. So innovation there are 4 things you need to be in order to be an innovation. Number 1, it's not just a discovery or an invention. That alone is not an innovation. Second characteristic is that if adopted, it will change the way we live. That's innovation. The third one is that it almost always is the result of team effort. Again, it's not a discovery or an invention. Right? It always involves the work of a team. And then finally, it almost always involves multidisciplinary approaches. So to have all 4 of that's an innovation. So I think at Chinese University of Hong Kong, Dennis, you asked about that, and I won't talk about you because that would be a conflict of interest since you're here. It's too well known. I don't need to talk about Dennis. Obviously, he's an example. But the way we have done it is that we encourage our faculty members to really pursue, sort of give them a lot of freedom of thinking. Anybody who can tell you, who can predict the future is lying, right? But on the other hand, if you think really hard and pursue the ideas that you have and you interact with others, then things will happen. Now, the key thing is that when it happens, that there is a mechanism to capture this incredible event and let it grow and blossom. And the results of people at CU, of course, has a long history. I certainly wouldn't want to claim any credit whatsoever, but I can tell you that we have done very well in terms of nurturing our innovators so that their products, their ideas, their achievements can be translated. We have examples such as SenseTime and SmartMore, just to name 2 unicorns that came about based on work done at CU, by CU faculty, by Chinese U students and postdoctoral fellows. And we will continue to do that because what we try to do is that to create an incubator space. I don't mean physical space necessarily, but a spiritual or conceptual space so that when they have something like this, it's not like, oh, gotta publish. But we let them incubate this so that it can ripen into a very practicable solution to improve the way we live. And again, there are many other examples. I certainly don't want to exclude any others, but it will be too long to describe. But I think we've done it right. We are actually constantly looking at how we've done it so that we know we can expand the things we do just right and maybe eliminate or reduce the things we don't do quite right. So we're happy what we have, but we want to be even better. Thank you.
Thank you. Alex?
Thank you, Dennis. For the mission of a university, I mean, it's very obvious that it's first education, then research, and increasingly it's knowledge transfer. So in Hong Kong Baptist University, we actually set up, as a long name, let me make sure I got it right, okay, Institute for Innovation, Translation, and Policy Research. What we recognize is that while researchers are very good, the KPI, so to speak, right, for most researchers is to have the result in publications. Now, the role from scientific publication to actually application is really long. I mean, there's something called the Innovation Readiness Index, from NASA, a Technology Readiness Index, TRI, back in the 70s, and they have 9 levels. Basically, the first 3 levels about research done in a university, bullseye research and that type. The last 3 levels, 7, 8, 9, done in the industry. The middle one, the so-called translation one, that's actually very hard. There are a lot of nickname for that, Dead Man's Valley and so on. And a lot of times, the one that can do well, in terms of the basic, research, are not good at doing a translation. And they tend to, in general, the scientists will think that the translation part is easy. And also they're seeing that there's a lot of potential, making a lot of money, they worry somebody will, quote-unquote, steal their work. So there's a lot of hand-holding to walk this basic research through, this so-called Death Valley. And different disciplines, very different. ICT is easier, for ICT type innovation, information and communication technology. There's a lot of talk about, you have undergraduate, you have research student, postdoc, they set up a few company and then they will do well. But then when you get to, then it's your field, biological science, the investor will not trust a postdoc. They need big scientists like you in order to be able to, attract the funding. So in a way, we ourselves assess the work by various professors, and then if we believe there's potential, then we will so-called walk with the professor to help them set up a spin-off, talk to the VCs, and it depends on how much our colleagues, academic colleagues want to move on the more practical directions. If not, we find the right person to help him or her to support them. That's how we promote, translation in Baptist University. Thank you.
Thank you. Now, so while we are embracing this translation, commercialization, entrepreneurship, just now in a number of the talks, like that from Professor Jiang Yaping and also Professor Vivian Yam in the InnoHK session, they warn about the need to still actually do the basic research, because that is, after all, the origin of all those ideas in the first place. So how can we actually strike this balance? So,
I think the issue is not, at this moment in Hong Kong, it's not an issue of striking a balance. In Hong Kong, of course, our basic research, I guess we have very high standard scholars. Whether Hong Kong's basic research is actually that good, in relative terms to other universities, I don't know. I cannot assess. I think because given that we don't really have major facilities, you don't really make great discoveries so easily, So I think we have to be realistic. But nevertheless, Hong Kong's basic research, of course, when we talk about basic research, there's always a lot of different understanding what that is. So basic research, in my view, is not basic science. Basic research is all the research done in different disciplines. that is aimed at creating knowledge, which is the output of which is mainly publications. So in my view, this is basic research already. Otherwise, only physics, chemistry, or math people will do research in which is basic research. Now, once you see it this way, then a lot of the so-called basic research should also be mission-driven. They have a purpose, to begin with. There's, of course, I'm an engineer, so there is, of course, curiosity-driven research, which is important, but I think in this world nowadays, in Hong Kong, mission-driven research is more important. So the issue is not a balance, because really we don't have enough in translational research. So the issue is to increase in translational research. This does not mean we should not further enhance our basic research, as I've said. I think our basic research also has weaknesses in many areas. But we have very good scholars. That's the strength. So enhance basic research, provide a lot more support for applied research, translational research.
Thank you. Rocky.
Yeah, thanks, Dennis, for that question. This is probably going to be an eternal question, how to balance basic research and applied or useful research. My answer to this is actually, there are only two kinds of research: applied research and not yet applied research. Now, the not yet applied research may never get to the applied research, but it's okay, because everything is built on knowledge. And knowledge can only be obtained through the process of curiosity. And knowledge is a continuous pipeline. You have a faucet on the top, knowledge comes down, and you have a bucket in the bottom, and that is the application itself. Anywhere along this pipeline, if there's a leak, if there's a broken point, then all that knowledge you get will never get there. Now, sometimes the knowledge drips somewhere into another conduit, and so you don't end up getting any water. But I am convinced that unless you have water coming from the top, you're not going to get any water in the bottom. Now, I mean, a good example, I think relevant to everyone here, is what's her name? Katalin Karikó, right? So she was the pioneer in mRNA-based approach to blocking things that you don't want, right, in the body. Now, I don't think she started thinking about making vaccines. For 20, 30 years, she was ignored, she was belittled, and she faced a lot of career difficulties because no one took what she did seriously. And I don't have to convince you why today that research is so important. Probably saved a lot of lives, and to just mention one fact. So here's an example of basic research. Out of curiosity, she thought that because DNA goes to mRNA, goes to protein, and protein do the work, whatever the work, bad or good. So if you can find some other molecule that's not the original mRNA, and you can shove it in, and you can interfere with the golden dogma, and you can block the reaction, then you will have something. I think it was based on really curiosity-driven, hard work. Nobody gave a damn to what she said for quite some time, and we see that. So I think there are only two kinds of research: applied research and not yet applied research. So I think as university, we should be very open-minded, sometimes even forgiving maybe, and allow both to thrive. The balance, I think it really is depending. If there were no COVID, maybe the mRNA story will not blossom so fast. So anyway, just my thought. Dennis.
Thank you. And then Alex.
Right, I just saw time's up, okay. Okay, we, as good academics, we get into definition. What is, basic research, and I'll change it to curiosity-driven research. As Rocky, briefly pointed out, in a way, it might just interest the scientist himself or herself, okay? Satisfies own curiosity. And then so-called application-inspired research. So you have something in mind you want to do. Now, I'll look into a lot of type of basic research, a lot of impact. But then turn around, you look at the efficiency, okay? Someone come up with a crazy idea that nobody really buy. It is indeed very, very basic. It's some curiosity. We understand about nature. How much money you give that person to do, okay? Okay, he or she is willing to sacrifice his own career for that. But then it might nothing come out of it. So I think using, how to use public money, okay, to fund research, the so-called curiosity-driven, on the surface, okay, that, it really satisfies the curiosity of maybe a few individual scientists, okay, or something that we have everything in mind if you can solve that problem, or even if it's partially solve that problem, you got benefit to society. Then how to use your public money to fund that? I think that's actually the real question. Now, depending on who you talk to. You talk to the curiosity-driven group, then they will tell you that mRNA research, Socky junction, how it changed the world. You tell to the industrialists, they say, I don't know what those scientists are doing. I need my problem solved yesterday. So there is, I don't know where I got that number when I was young, okay. Somehow I got impression in stateside that it's not a golden ratio, okay. It's sort of like a pyramid, 1, 10, 100. So every dollar that somehow someone spent, maybe government or private, okay, on basic research for a healthy, economy, healthy setup will be $10 on the applied research, or application-driven research, then another 100 on the industry research. The key point I don't think is really application-driven research or basic research. It's rather going back to the point I made earlier, the translation part. Because whenever we talk about research in the university, then the KPI will be publications, okay? Because when you guys are about expert, okay? I don't want to use example, but you can have very good results on a petri dish, okay, on your lab and so on. But if we want to make it into a pill that a patient can swallow, before you even go to clinical, there's a lot of work to be done, toxicology tests and so on. Very few people fund that part of the work, okay? You can certainly cannot get money from RGC. And then the big pharma, the pharmaceutical, are not interested in investing in those work because chances are nothing will come out from those work. So that gap needs to be filled if you want to translate work in the university, whatever, how you label it, into the real applications. Thank you.
Okay, thank you very much. So with that, I think we'll draw this session to a close, and I look forward to walking down this path of innovation with each and every one of you. So thank you very much for your time.
Thank you very much once again to Professor Low and all our panel members. Thank you. Please remain on stage. First of all, I would like to invite all of you to make one step forward. And we're going to take several photos here on stage, actually. And before that, you may want to get ready to have your mask off if you wish to. And while our presidents are getting ready, I'm not sure if you know, but our president actually have a meeting this morning in Wan Chai. That's why they couldn't join us in the morning. And at this juncture, we would like to invite the following guests to come on stage and present them a crystal block as a token of appreciation. Now please welcome on stage Secretary for Innovation, Technology and Industry, Professor the Honorable Sun Dong. Please welcome. Of course, our Commissioner for Innovation and Technology, Ms. Rebecca Pun, please welcome on stage. As well as Undersecretary for Innovation, Technology and Industry, Ms. Lillian Zhang, please welcome. All right, before presenting the souvenirs, let's first have a group photo. All right, please smile for the cameras at the center. All right, just for the information for our audience, this crystal block actually is presented by Innovation and Technology Commission, and all the other speakers have already received them during the lunch break just now. And taking this opportunity, we would also like to express our gratitude to all the presidents joining us today here. They actually rushed back for our session in the afternoon. Another big round of applause to our presidents, please. And now, please bring out the souvenirs to Secretary Professor Sun Dong to present for us. We'll have one guest to receive one of the crystal blocks. We'll have all the crystal blocks for all the speakers. The presidents are really supportive to our event today. Thank you very much for making time to join us. Thank you so much. Let's have another photo together. Please smile for the camera at the center. Okay, a few more. Definitely a moment to remember. And well, very fruitful discussion just now, really. We learned so much about how it's going to move forward later on. Thank you so much, everyone. Please be seated. Thank you. Thank you once again to all our presidents and, of course, to also Professor Low for moderating the session for us. Thank you. Thank you very much. That was really a very insightful discussion. Now, let's switch gears and move on to the keynote session for this afternoon. We're honored to have China's father of quantum, Professor Pan Jianwei, Executive Vice President of the University of Science and Technology of China, to share his keynote speech through video on Dream or Reality, Quantum Communication, the Past, Present, and Beyond. Let's welcome Professor Pan.
Ladies and gentlemen, good afternoon. First of all, I would like to thank the organizer for the invitation, which gives me a chance to present my views on emerging quantum technology. Before my talk, I would like to first congratulate Alan Archipect, John Clauser, and Anton Zeilinger for winning this year's Nobel Prize in Physics for experiments with entangled photons, establishing the violation of Bell inequality and pioneering quantum information science. This is very inspiring for the whole quantum community. I am also very happy and proud to see some of our work were also mentioned in the presentation of the press release. Meanwhile, the 2023 Breakthrough Prize in Fundamental Physics goes to 4 pioneers in the field of quantum information. Their idea laid the theoretical foundation for quantum information. Since a practical quantum computer is still far away, in the following, I will mainly present a brief overview on history of the quantum communication and show you how quantum communication has developed from a pure theoretical idea into a preliminarily mature technology after more than 40 years effort of the community. In quantum computation, our community set 3-stage goal towards the ultimate realization of a practical quantum computer. So the first one is called quantum computation advantage, which means the speed up is so overwhelmingly huge that no classical computer can perform the same task in a reasonable amount of time and is unlikely overturning by classical algorithm or hardware improvement. The second one is to construct a quantum simulator to efficiently mimic the evolution of a complex quantum system, such as the mechanism of high temperature superconducting and so on. So the third and the final goal is to realize universal and programmable quantum computer with the help of error correction. So in recent years, several groups from the United States, China, and Canada have claimed the implementation of quantum computation advantage. In 2019, Google first announced quantum computation advantage with the 53 superconducting qubit quantum processor Sycamore. Though recent study has shown that a million noise sample generated by Sycamore in 200 seconds can actually be generated in a few tenths seconds on a state-of-the-art classical computer. So in 2021, we built the quantum processor 主冲之 with 66 superconducting qubit, the achieved sampling task is about 6 orders of magnitude more difficult than that of Sycamore. Using photons in 2020, we realized Gaussian boson sampling on an optical machine 9张. 9张 detect up to 76 photons, and its sampling rate is about 100,000 times faster than classical supercomputer with the current best known optimal classical algorithm. Last year, we upgraded the optical network from 100 mode to 144 mode with the detect photon number up to 113. Most recently, the detect photon number has been scaled up to 250. So this year, Canada company Shenandoah also realized a photonic quantum processor with 216 squeezed mode. Similar to Google's roadmap, we hope to build a logic qubit which need about 1,000 physics qubit in next 3 to 4 years, and then scale up the system while keeping each of the physics qubit with high quality. It is foreseen that in 10 years, what might be possible to build up an error-corrected quantum computer with about 1 million physical qubits. One can see that a practical quantum computer is still far away. As a contrast, quantum communication is the first practical quantum information technology. Achieving secure information transfer has been the dream of human beings since ancient times. However, historically, advance in classical cryptography has been defeated by advance in cracking. For example, due to the Second World War, Alan Turing cracked the Enigma cipher machine. Moreover, in modern cryptography, such as the widely used public key encryption system, RSA 512 was cracked in 1999, RSA 768 was cracked in 2009, and even RSA 1024 has been considered unsafe. Since all the classical encryption methods can in principle be cracked, it has been long suspected human ingenuity cannot conquer the cipher, which human ingenuity cannot resolve. So an everlasting question is, can we invent a cipher tool to ensure secure information transfer? As suggested by quantum physics, a possible solution is to explore quantum superposition. As we all know, in our everyday life, a cat can only either be in alive or dead state. However, according to quantum superposition principle, a cat in the quantum world can even be in the coherent superposition of alive and dead state. When we apply quantum superposition principle to multi-party systems, we are led to the conception of quantum entanglement. For example, two cats in the quantum world can even be in the coherent superposition of alive, and dead state. So physically, any two-level quantum system can be used as a realization of a qubit. For example, we can explore the two polarization state of a single photon to encode 1 bit of information. Then for a system consisting of 2 photons, they can be in one of the following 4 Bell states, the so-called maximally entangled state. Quantum key distribution is the best known quantum communication protocol. For example, one could explore the BB84 protocol to implement single photon-based key distribution. With the help of the shared secret key and one-time pad encryption, one can achieve unconditional secure communication. So quantum teleportation is another interesting application of quantum communication, which is a way to transfer an unknown quantum state from one particle to another without actually sending the particle itself. This is very much like the way to achieve Star Trek in science fiction, although nowadays it's far, far away from teleport a person. It is visible to teleport various quantum states in a network, which is an essential ingredient for quantum computation and distributed quantum network. Interestingly, the state of one particle of an entangled pair can also be teleported. For two entangled pair, 4 and 1, 2 and 3, if we perform a biostate measurement on particle 1 and 2, as in the teleportation protocol, then the remote particles 3 and 4 that never interacted can be entangled. This process is called as entanglement swapping, which plays an essential role in long-distance quantum communication. So the first proof of concept demonstration of QKD and teleportation were done in 92 and 97 respectively. From here you can see the achieved distance at that time are quite short. Both are only about 30 centimeters. So by 2005, several groups have demonstrated quantum key distribution over 100 kilometer fiber. However, it was found due to the imperfection of realistic quantum device, mainly due to imperfection of single photon source and imperfection of single photon detector. There are serious security loopholes in all previous experiments, making the secure distance of quantum key distribution was limited to the order of 10 kilometers in fiber. So therefore, there are two major challenges towards large-scale secure quantum communication before we can finally promote any practical application. First, we need to overcome the security loophole caused by imperfection of realistic device. Second, we need to extend the distance. In fact, due to exponential photon loss in quantum channel, it is extremely difficult to achieve quantum communication over larger distance. For example, in 1,000 kilometer telecom fiber, even with 10 gigahertz single photon source and ideal single photon detector, only 0.3 photon can be transmitted on average percentually. So to solve the security loophole caused by non-ideal single photon source, decoy state QKD method was proposed in 2005. In 2007, two independent teams, including us, implemented decoy state QKD over 100 kilometer fiber. So in 2013, following the scheme suggested by Hao-Kwan Lo, we demonstrated measurement device independent QKD to close the loophole caused by imperfect single photon detector. Very recently, the secure distance of QKD in field fiber has reached more than 500 kilometers. So with MDI QKD and a controllable DIY source, as pointed out by Charles Burnett in measurement device independent QKD, if the untrusted device remains outside Alice's and Bob's trusted enclosure, they need only trust themselves not to have inadvertently created a side channel to Eve through incompetent design of their DIY light source. Therefore, information theoretically secure QKD with realistic device can be approached properly. So at present, the longest distance of MDI QKD in field fiber is about 500 kilometers, while the longest distance of quantum teleportation at the ground is around 100 kilometers. So how to extend the quantum communication distance further? One possible solution for large-scale content communication is content repeater. So the central idea of content repeater is to solve the problem of photon loss via entanglement swapping and to solve the problem of decoherence via entanglement purification, where entanglement purification is a way to detail a subset of highly entangled state from a larger set of less entangled state. Experimentally, it imposes three major requirements: entangled swapping and entangled purification with high precision, and quantum memory with high performance. So the first entangled swapping experiment was demonstrated in 1998, and in 2003, we proposed a visible entanglement and we implement fault-tolerant entangled swapping via high precision four-fold interferometer. So in 2001, and we proposed a visible entangled purification protocol with linear optics. Late in 2003, we managed to experimentally demonstrate high precision entanglement purification. So the reason why we need a quantum memory is that without quantum memory, the cost of resource in multi-stage realization is proportional to 1 over p to the power of 2n, where p is the probability of emitting entangled photon pair in each experimental run. Thus, is not scalable. However, if we know when the photon pair is created and can store them on demand, then the total cost to implement entangled purification and swapping is proportional to 1 over p squared. So in this way, we can achieve efficient distribution of quantum entanglement between distant locations. So in 2008, we experimentally realized a robust quantum repeater scheme, which only requires stability on the order of a few tenths centimeters by making use of two laser-cooled atomic ensembles which are connected through a 300-meter fiber. However, the memory performance at that time was very poor. So in order to enable long-distance quantum repeater, both the lifetime and high retrieval efficiency has to be improved significantly. So in our 2008 experiment, the lifetime is only about 1 microsecond, and the retrieval efficiency is only about 35%. From this figure, it implies the lifetime had to be improved by 8 order of magnitude in order to fulfill the requirement of 500 kilometer quantum repeater. Since then, many experimental improvement and development have been carried out. In 2016, we managed to prolong the lifetime to a few hundred milliseconds, while still with high retrieval efficiency up to 76. So in principle, the new result already support quantum repeater enabling quantum communication at a distance of 500 kilometers. Moreover, to connect quantum memory node with fiber, one needs to shift the atomic wavelength to telecom wavelengths. So with the developed frequency conversion technology, we successfully achieved quantum entanglement between remote quantum memory over large distance. However, it is foreseen a practical quantum repeater at 1,000 kilometer scale might still need 10 more years. So before the realization of practical quantum repeater, a partial solution is to use trusted relay to connect metropolitan network with fiber. So in the end of 2016, and we established the world's first intercity quantum communication backbone with 32 trusted relay at a distance about 2,000 kilometers from Beijing to Shanghai. So the backbone is currently used for financial application, public affair, and so on. So another promising solution for global scale quantum key distribution is through satellite in space. The satellite to ground connection has significantly reduced photon loss. This is because the effective thickness of the atmosphere is only about 10 kilometers. So most of the photon pass is in empty space with very small absorption and turbulence. So since 2003, we have spent more than a decade in performing systematic ground tests for satellite-based quantum communication. So in 2004, we did the first ground test on distribution of entangled photon over 13 kilometers in Hefei City for the first time, well beyond the effective thickness of the allosphere. So in 2011, we demonstrated both entangled distribution and quantum teleportation in Qinghai Lake over 100 kilometer free space, which verify the visibility of quantum communication via high loss satellite to ground channel. So in 2012, we performed a full-scale verification of satellite to ground quantum key distribution under various simulated conditions of rapid motion, vibration, and random movement of the satellite, turbulence, and high channel loss, overcoming all the demanding conditions for ground satellite QKD. Through this ground-based experiment, we have mastered the key technology of quantum communication with low orbital satellite. So on 16th August 2016, the world's first quantum satellite MISSILS was launched successfully. So the MISSILS has three major scientific missions. So the first mission is to achieve QKD between satellite and ground station at a 1,000 kilometer scale. So in the experiments, the observed final key rate is about 1,000 bits per second, which is 20 order of magnitude higher than using fiber channel at the same distance. In the second experiment, and we managed to achieve satellite-based entangled distribution between two ground stations, which are separated with distance 1,200 kilometers. In the second experiment, we managed to perform the first space-scale test of spook action under strict Einstein locality condition. And the third mission, we managed to achieve quantum teleportation from ground to satellite over 1,400 kilometers. Later, using missile satellite as a trusted relay, an intercontinental QKD between Beijing and Vienna over a distance of 7,600 kilometers has been realized. Recently, we successfully implemented QKD between missiles to Gagarin and in Canada. Meanwhile, cooperation with Italy, India, and South Africa are also development. So in future, it is foreseen to establish a global quantum communication network by combining metropolitan network, intercity quantum communication connected by quantum repeater, and long-distance quantum communication with quantum satellite. So the 5 basic metropolitan network is mature and practical. For quantum repeater, it is foreseen to support quantum communication at a distance of 1,000 kilometers in 10 years. As to the satellite-based quantum communication, there are still several technological challenges need to be overcome. For example, as a low orbital satellite, missiles cannot cover the whole Earth directly, and it can only work in Earth's shadow. So the solution is to form a quantum constellation with multi-low orbit satellite to build a more efficient network, and with GEO satellite to achieve much longer mooring time to distribute many more keys than LEO satellite. So to do so, a pre-requirement is to ensure satellite work in solar radiation background. So in 2017, we have relied the long-distance free space QKD in daylight to confirm the visibility of Corning constellation. To implement a practical Corning constellation, we need a lower cost microsatellite, such a lightweight payload. Recently, we have realized small size QKD payload, which is only about 20 kilograms. The first microsatellite for Corning communication was launched this July, most recently. And we also developed a portable ground station with a weight less than 100 kilograms, with which mobile connectivity distribution can be supported. So the first GEO satellite for Corning communication is currently under development, which is scheduled to be launched around 2026. Besides QKD, our GEO satellite will also carry on an ultra-price optic clock with a fractional instability up to 10 to minus 19, which can provide precise timing information sharing with a much better long-time instability, which could be 4 orders of magnitude better than the microwave time sharing, thus providing a new definition for the fundamental time unit second. Moreover, in outer space, the magnetic and gravitational noise are negligible, so the fractional instability of optic clock may even reach 10 to minus 21. So with ultra-price time information sharing network and long baseline interferometer, we hope it will be possible to provide a new plot for fundamental physics, such as hunting for dark matter and detecting middle-band gravitational wave. Thank you for your attention.
Thank you very much, Professor Pan, for enlightening us. Thank you very much. Well, ladies and gentlemen, that brings us to today's last yet another much anticipated session of today's summit, Dialogue with the Younger Generation, Unlocking the Limits, Road to Innovation. Well, before the session, I would like to invite all of you to actually scan your QR code because we welcome questions from the floor. A Q&A gateway has been set up for you to submit your questions if you have any. You can either scan the QR code at the back of your badge to access the gateway, or you can also simply raise your hand later on in the interactive session, and we're going to answer your questions or ask our speakers to address to your questions. Well, now, without further ado, please join me and welcome on stage our speakers. Joining us physically here, we have Dr. Kenny Chan, Associate Professor, Department of Biomedical Engineering, City University of Hong Kong. Please welcome. Thank you. Next, we have Professor Vic Law, Professor of the Department of Physics at the Hong Kong University of Science and Technology. Please welcome. And then we have Dr. Stephanie Ma, Associate Professor, School of Biomedical Sciences, the University of Hong Kong. Please welcome. We also have Professor Anderson Shum, Professor, Department of Mechanical Engineering, the University of Hong Kong. Please welcome. Please take your seats. And once again, a warm reminder, we can go face mask with the mask off if we wish to. So if you want to, you can get ready at the moment. Well, aside from our guests here joining us physically, we also have Professor Ben Thompson, Professor, Department of Optometry and Vision Science, University of Waterloo, who will share with us through a video. Now, let's start with Professor Thompson.
Hello, it's fantastic to be part of today's session, and I'd very much like to thank the organisers for inviting me. And today I'm going to talk about pathways to innovation. In my current role, I am the CEO and Scientific Director of the INNOHK-funded Centre for Eye and Vision Research. And in our centre, we are innovating new technologies to improve eye and vision health. So innovation really forms the core of everything that we do within the Research Centre. I'd like to focus on two key terms that we have in our vision statement for the Centre for Eye and Vision Research, that you can see here on this slide. And these are research, creativity, and collaboration. And these are two core components of pathways to innovation that I see in my own experience, particularly at the R&D stages of developing new technology. So I'd like to just talk a little bit more about these two key concepts. Research creativity, in my mind, has three key components. First of all, you have to have a strong foundation in the area that you're interested in. You need to know the basic underlying science and technology that already exists in order to be able to identify the gaps and to form new connections when new opportunities arise. So following on from that, you need to have an open mind. Listen to people from other disciplines. Take the opportunity to attend symposiums that are outside of your areas of interest. See what else is happening in the scientific and engineering community around you in order to start to make these new connections. And then when you find or identify a new connection, actively seek out new opportunities to connect with people in different disciplines and to bring them into your area of interest. So this is really going in full circle, going out to connect with new people and then to be able to talk from a foundation of strength of your knowledge in your area of interest. Now, in addition to research creativity, we also have collaboration. Obviously, these two concepts are closely related to one another. In collaboration, once we've made these new connections, we need to work together to form a new innovation team. Now, this often takes time. Typically, people from different disciplines will use different types of technical language, different types of jargon to communicate ideas. We have to take time to learn how to communicate with one another, to find common ground, and then to bring our shared expertise together in order to advance knowledge and to innovate. Now, importantly, these new collaborations can be focused on a very, very specific question, but they can also be curiosity driven, the sort of experiments that start with, wouldn't it be interesting if something happened? Typically, curiosity driven research over time will coalesce into real world applications and new innovations. So I'd like to give you an example from the Centre for Eye and Vision Research that brings together these core principles of research creativity and collaboration. And it's a project that is being conducted between my research group, which is interested in visual perception and neurorehabilitation, and the quantum physics group at the University of Waterloo. And we got together after meeting at a symposium where we were talking about our different areas of research. And the quantum physics team came to me with a new invention that they had created, which is a particular type of structured light laser beam. And you can see it on the left-hand side of this slide here. What they've done is been able to wrap polarization or directional light helically around the beam in a corkscrew pattern. And they can change the number of those wrappings in order to encode information within the beam. And they came to me because they were interested to know how this beam might interact with the human eye. And we developed a study where we thought, well, wouldn't it be cool if we could tell whether or not the human eye can detect quantum states of light? So this was a curiosity-driven research experiment. So we set up the experiment, we formed a team, we found a way to communicate together so that we could set up the measurements of the human visual perception and also set up all of the physics apparatus that was required to conduct the experiment. And in fact, we found that when people look at this beam, it actually interacts with the nerve fibers and the pigments at the back of the eye, and it projects an image onto the retina that people can see. And on the right-hand side of this slide, you can see the type of image that people perceive. This is actually the quantum light beam that's been recaptured as reflected light from the back of the eye. So we spin the beam around, and the number of these fringes in the pattern that you can see here indicates the number of wrappings or the quantum information in the light beam. So this was a new discovery that was extremely interesting. So now that we had our new discovery, our innovation, we now need to apply it. And this has led to a project within the Center for Eye and Vision Research, where we're studying the use of this structured light beam for diagnostic imaging of the eye. We're currently collecting data from patients, and we're seeing promising results suggesting that this type of imaging could lead to the early detection of macular degeneration and the delivery of sight-saving therapy. So just an example of where creativity and collaboration can come together in a real-world project. Thank you very much for your attention.
Thank you very much, Professor Thompson. That's very interesting sharing there. So we have 4 bright and young academics to be here with us, and I know you have something to share with us as well. So why don't we start with Dr. Candy Chan?
First of all, I would like to thank the organizer for the invitation so that I can share with you my road to innovation. Here, I would like to talk about the molecular imaging, how we can use it, the MRI, to monitor brain health. So the brain is our most important organ in our body because it helps us to communicate, make decisions, solve problems, live a productive life. So it's worth our efforts to protect it from the early stage of life to the late adulthood. And this helps us to maintain mobility, mental, and cognitive function, as well as minimizing risk to the following diseases, such as vascular disease and degenerative disease, as well as mental illnesses. So to monitor our brain health, it's very important we have a robust tools to monitor the molecular changes or abnormality at the molecular level, as shown here. So because if the disease progresses to the organ level, typically it's a mid-stage or late stage of the disease. So molecular imaging definitely helps us to predict disease and also to have precise diagnosis and treatment. So among the clinical imaging modality, MRI is the only modality that enables us to detect molecules without using radiation. So the uniqueness of MRI is just that it detects the little protons on the water molecules. Then you can appreciate that how well we can see our brain as shown by the images below. Sorry about that. So you can see the great structures, anatomy, and also the function connectivity, as well as the molecular information. So here is just a video to show you how well we can see our brain. So this is basically the wiring in our brain through an advanced MRI called diffusion MRI. So you can see that there are billions of signals that are transmitting, and then as well as with the color coding, we can see how the electrical signal is transmitted up and down, back and forth, and left and right. Then we can also see the fiber density. So in our lab, we basically make use of advanced molecular MRI called CEST MRI. The goal is to achieve diagnostic. That means diagnosis and treatment at the same time. So we focus on this area, including cancer, neurodegenerative disease, and the regenerative medicine. So typically, we take 3 steps in order to guide us through this process. So first, we identify and define the problem. For example, for cancer, if we want to track the drug delivery, then we can then check what are the real problem, what drug to deliver and to which part of the body. And then we'll find the solution across discipline. So multiple speaker has already mentioned the importance of interdisciplinary or multidisciplinary research. So then we will look at through chemistry, what are the drug, and also what imaging approach we are going to apply. Then we prove and refine the concept through experiments. So I will show you a third example how we unlock the power of molecular MRI to fight brain cancers and Alzheimer's disease. So one of the challenges in treating brain cancer is that how we can have an effective means to deliver drug to the brain because of our brain are well protected by the blood-brain barrier. So you can see that there are many ways invented by the researchers. The most non-invasive one is the intranasal drug delivery. So recently we developed an approach that with this little carrier, then we can effectively deliver the drug from the nose to the brain. So as you can see the first panel, we can see the drug distribution when it arrives to the brain. And the second panel, you can see the drug delivering vehicle delivered to the brain. So by using the power of the molecular imaging, we can also see the drug release in the brain. When we implant some of the therapeutics into the brain, then we can monitor the B panel showing you the drug release profile, and then the C panel showing you the drug delivering release profile. So you can see the drug release slightly faster than the drug delivering vehicle. So another important parameters related to the molecular aspect when we are treating cancer is the pH, because aggressive tumor also comes along with a low pH. Here we use the microfluidics approach to develop this pH sensing like microbits, so then we can monitor the pH changes during treatment. So now let's move on to the Alzheimer's disease. Everyone knows Alzheimer's disease affects over 50 million people worldwide. And in Hong Kong, this number will reach up over like 300,000 by the year 2039. So right now we are diagnosing Alzheimer's disease at the mid-stage of disease where the brain already has like some significant loss of neurons and then symptoms has occurred. So definitely we need a much earlier biomarker. So recently, research findings suggested that reduced cerebral spinal fluid clearance and actually has led to the A-beta formation, the plaque formation. This basically brings a very controversial question to the field: is A-beta is the real problem? And further studies suggested that the reduced A-beta clearance actually occurred 20 years before symptoms appeared. So with our pioneer technique about using the molecular MRI to detect glucose, recently we and collaborators from Hopkins developed advanced MRI to detect the glucose signal in the CSF. So here is like some of our findings. Can I play the video? Sorry, it's not working, but it's okay. So the first one is showing you the normal mouse, and then the second one is the AD mouse. So from the video, basically you can see a slow clearance over time. So the clearance rate in the AD mouse is 3 times lower than that of the normal animal. Oh, okay, it's coming. So just a, okay. It's okay. So then we also developed a deep learning approach to facilitate us to detect this subtle and molecular change at the early phase of the disease to facilitate Alzheimer's disease detection. So some of the early hallmarks in AD, in addition to A-beta, we shouldn't overlook is like reduced CSF clearance, lymphatic dysfunction, altered glucose metabolism. And we believe the advanced molecular MRI platform could provide valuable information about the early molecular changes, so unlock the power of molecular imaging to precision medicine and disease prediction. We would like to thank lab member, local and overseas collaborator, and the funding source, and especially the Hong Kong Coach Center. Thank you. I'm happy to take questions from you.
Thank you very much, Dr. Kenny Chan. Thank you for sharing your work with us. Well, before Q&A session, we're going to have other speakers to share with us first, and we'll move on to the interactive session later on. And now let's hear from Professor Vic Law.
Thank you. And first of all, I thank ITC for giving me this opportunity to have a dialogue with the young people. And we were supposed to talk about inspiring stories to inspire the young people, and my own story is a bit boring and humble. So I decided to talk about the story of John Bardeen. And I'm a theoretical physicist from HKUST. And so the story I would like to talk about is about John Bardeen, who was born in 1908. And he's the only person in history who is awarded the Nobel Physics Prize twice. And in this afternoon, our presidents of the universities were discussing about applied and curiosity-driven research. And Bardeen had done both. And that got him 2 Nobel Prizes. And the first one was awarded in 1956. And that was for the invention of transistors. You all know transistors. So, and he's one of the 3 inventors, which I will talk a little bit more later. And actually, on his way to Stockholm, in 1956, he came up with an idea to explain this unsolved problem of superconductivity on his way to Stockholm. And that won him the 2nd Nobel Prize. So the first one of his Nobel Prize was really about, he had a problem, practical problem in mind. Because electronic circuits was a big deal in the first half of last century. As you know very well, that was the time of some giants of inventions. Thomas Edison, Nikola Tesla, and that was really the time of invention by then. There was a need of electronic circuits, and for electronic circuits, you need switches and amplifiers. And the transistors, not the transistors, actually those vacuum tubes you see on the pictures there, they play the role of these switches and amplifiers. And they are quite big, actually. And it can be as big as your fingers. So, and these vacuum tubes built out of, were inspired actually by Thomas Edison's invention of light bulbs. That's why they look like light bulbs. And these switches actually were very useful. You could actually build computers out of it. And this is one of in the figure, this is one of the first computers, programmable computers. And so it has 18,000 vacuum tubes in it. For some calculations, it is thousands times faster than human. So it was claimed by that time that one of these machines can replace the 2,000 smart people for doing some certain calculations. So people were really excited about it. But if you look at it, they are quite heavy, they are quite big. This machine is 27 tons, and it occupies a space of 170 square meters. And it consumes 150 kilowatt, which is like you turn on 100 hair dryers at the same time. It consumes a lot of power, it's really heavy and something like that. So Bardeen was trying to solve this problem. And it was not easy. So, but Bardeen, he took, he's a physicist, and if you look at his PhD thesis at Princeton, so he was studying solid-state materials. He got his PhD in year 1936, 6, I guess. So that was actually not that far away, only actually less than 10 years, when quantum mechanics was formulated. But he used this knowledge of quantum mechanics to understand solids. And then he worked at Bell Labs, and together with Shockley and Bardeen, these three people, they invented this so-called point contact transistor, which were much smaller, only 2% the size of vacuum tubes by that time for the prototypes, and also much energy, more energy efficient. And this is very important that, and Shockley took this invention, improved it, and he went to Silicon Valley and opened a company called Shockley Semiconductor, as you can see in the picture. And that was the year that he got the Nobel Prize in physics, together with Bardeen and Brechton. And then out of this company, 8 employees of Shockley formed the Fairchild Semiconductor Company. And then basically the Silicon Valley was born there. Intel and AMD and these companies all basically were formed from the employees of these companies. So that really changed. Now nowadays we have billions of transistors in a CPU. That is because the invention of Bardeen and the others. And in the year of when Bardeen won the Nobel Prize on his way to Stockholm, he had a very curious question to explain this phenomena of superconductivity, which is some materials can conduct electricity without any resistance. And as you can see here, that was the paper was published in 1957, and that won the three gentlemen, Bardeen and Cooper and Schrieffer the Nobel Prize. And this theory was very important, and it did not just explain the theory of superconductivity, but actually inspire many branches of physics of how we understand the world. And importantly, I was talking about semiconductor transistors, from vacuum tube to transistors. And Professor Pan talked about this quantum computer. This is also related to Badin's invention, because nowadays, if you look at Google's quantum computer, and also Professor Pan's quantum computer, Zhichongzhi, they are formed by superconductors. And if you see in this picture, the crosses there, each cross is a quantum bit, and they are formed by superconductors. And this quantum computing qubits are very special because they can make use of this principle of quantum mechanics, which is called superposition. And a few of these qubits is already enough to do some computations, which cannot be done by classical computers. So this is a very active research area nowadays. And Professor Pan explained the power of quantum computers, and I'm not going to explain here. But quantum computers are very fragile. These qubits are very fragile. So nowadays, what we do for our research group at HKUST is to find quantum systems which are very robust and which can make quantum computers, and which can be components of quantum computers. And hopefully, we will have functionable quantum computers in the near future. Thank you.
Thank you very much, Professor Law, for sharing the road to innovation, the story of one of your inspirations, I believe. Thank you very much. Well, later on, we'll ask you for your tips as well. Now, let's invite Dr. Stephanie Ma to share with us. Dr. Ma, please.
Thank you very much. And I would also like to begin by thanking the organizers, ITC, for the very kind invitation and opportunity to share my research and also my thoughts on innovation. So cancer, as we all know, is a very deadly disease. And for the past 2 decades now, the scientific community has really pondered between the link of stem cells and cancer and how related research can lead to a cure. So we now know that all cells within a tumor are actually not all the same. And in fact, cells within the tumor can contain many different cell types, including, for example, cancer cells that are more proliferatively dividing and cancer cells that are more quiescent or dormant. So we and others have now shown that there exists a subpopulation of cells within the tumor that are called cancer stem cells. And these cancer stem cells are not what we often hear about normal stem cells that we use for anti-aging or regenerative medicine. These cancer stem cells are actually the bad guys, and they represent an important root of the disease and can contribute to therapy resistance and tumor recurrence. So cancer stem cells, like normal stem cells, they share unique properties to self-renew, which is to make identical copies of themselves, and also to differentiate, which is to make different cell types. Now, traditional therapy, like chemotherapy or radiotherapy, can initially shrink the primary tumor by killing off the non-cancer stem cells. But the cancer stem cells are very resistant, and they're more resilient to these therapies. And because of their unique abilities to self-renew and also differentiate, they're able to repopulate the entire tumor over time, and then basically causing tumor recurrence later on. So in the cancer research field, we have something called the hallmarks of cancer. Basically, you can view it as a holy Bible of cancer research field. And in the year 2000, it was the first edition of the Hallmarks of Cancer that was published with 6 hallmarks. And then 11 years later, in 2011, they published an updated version of this Hallmarks of Cancer where they added 4 additional hallmarks of cancer. And more recently, earlier this year, they also added 4 additional emerging hallmarks and enabling characteristics, which consist of unlocking phenotypic plasticity. Basically, it's related to cancer stemness. So if you view it in a normal setting, cells actually have a restricted ability to differentiate. And And this restriction will allow the cells to function better and to be also more organized in a specific tissue type. But in cancer, this restriction is gone. And now cancer cells can also change and adopt different differentiation states. And now we know that actually in cancer, a more undifferentiated state and a more stemness state can contribute to therapy resistance and tumor recurrence. And this hallmarks of cancer also beautifully illustrates that as much as we think we know about the disease, we actually don't know much. There's always new things to learn. And over the past 22 years, there are so many new discoveries from basic science that have stemmed to contribute to the identification of these hallmarks. And each of these actually have contributed one way or another to benefit patients, either in the form of a therapy or a better diagnostic or prognostic biomarker. So cancer stem cells, you can view them as like dandelions in your backyard. You can cut the leaves all you want, but unless you pluck out those roots, the cancer will keep coming back. And in view of that, my team is very much interested in looking at what are the properties of these roots to try to find better therapy for cancer. And we have dedicated much of our efforts in the study of a special cancer type that is called liver cancer, and in particular hepatocellular carcinoma. And it is a form of liver cancer that is very prevalent in Southeast Asia and with a very poor prognosis. But cancer is not just on cancer cells and cancer stem cells. There's just more to that. And in the tumor, we need actually an ecosystem that supports the cancer, and this is called the tumor microenvironment. So we now know, in addition to cancer and cancer stem cells, we also have blood cells, immune cells, and even non-cellular structures like the stroma that supports this entire tumor to ensure that it will thrive. And now we know that actually there's a link between cancer stem cells and also immune evasion, the one that Professor Mack actually alluded to on cancer immunology and ability of cancer stem cells to evade the immune system. So we're very much interested to also try to study this in recent years. Now, our lab is focused on the early phases of translational health research, but of course in more recent years, of course, and with our involvement with the Inno-Hong Kong centers, we're also very much mindful and trying to push some of our research discoveries in the lab into translational research work. But as we've heard at the President's Forum just now, I think we need to strike a balance because not all basic research discoveries can be translated, for one. And the second thing is not all scientists are suitable to be entrepreneurs in that. And so I think, but what we know for sure is that successful translational applications with societal impact all stem from sound basic research discoveries. So we must do innovative science, and I think this is definitely the key. But we have to be mindful that not all the basic research discoveries that we do may be able to be immediately translated into impact beyond academia or societal impact. But it is important to note that each of these fundamental discoveries can actually build form a core building block in science, and over time will help to piece the picture together. And I think this will also have to come with the efforts of our I&T ecosystem. So in addition to our research innovations, we must work with different stakeholders of the I&T ecosystem to help piece this puzzle together. So with that, I'd like to end by thanking my team and also collaborators. I'm very thankful for them for sharing the same passion with me. We find joy in what we do in the lab and for a topic that we hold close to heart. So thank you very much for your time.
Thank you very much, Dr. Ma. We definitely need more young minds and young people to join the industry and do more innovation for us. Thank you. Next, let's have Professor Shum.
Thank you. So first of all, I'd like to thank ITC for the opportunity to speak in this section. And also I'd like to thank all of you for staying this late to this summit. So I'm Anderson Shum. The topic that I was given was the Unlocking the Limits Road to Innovation. So I asked myself, what is the road of innovation? I think the road of innovation starts with a deep passion and interest in science. And why are we interested in science? So I asked myself, why are you interested in science? So here are a few thoughts that I'd like to share with the audience of my personal journey. So I think usually most people start with interest in science starting from curiosity. My work works on droplets, droplets like water droplets that you see every day from the faucet in kitchen, bathrooms, etc. So if you're curious at why droplets are coming out of the faucet when the flow rate is small, and then if you can form water droplets, then I started to think about, is it possible to form more sophisticated droplets? So my PhD research started working on a technology known as microfluidics, where we were using very small channels to flow fluids with better degree of control. And the consequence is that we can control dripping of water droplets from these microfluidic nozzles to make droplets that are very different from what you see from those faucets. For example, we can make droplet in drops. The video above shows water droplets surrounded by a layer of oil in a water environment. And the droplets below are some of the droplets that in our recent research we caused them to divide. It started from a question or curiosity of why cells can divide but droplets cannot. How can we overcome the limit so that we can get droplets to divide as well? So that is curiosity. Besides curiosity, I think another thing that sometimes drives us to do research is problems that need solutions. I think in the past 3 years, a lot of us are very familiar with why then the world needs solution. Because of COVID, a lot of us are very used to getting our samples tested. These could be from our swab, from the nose, but there are also other samples like blood, saliva, sweat, urine, etc. I'm not sure why the fonts came out weird, but I hope you bear with me for that. But basically, we collect a lot of these samples when we're trying to do diagnosis or screening, and then typically you put these samples in a test tube or in a microwell, and you try to do all kinds of assays to find out what you have inside. So in order to do it more efficiently for the need of maybe faster diagnosis results and higher sensitivities, we may need to think of other ways. And the way that you try to find out whether certain patients have the diseases is to look for certain biomarkers. So these biomarkers could be cells, could be antigens, could be nucleic acid and other small molecules. So antigens are what you're looking for with your RAT test, and nucleic acids are what you're looking at when you're doing the PCR. So these are present in patients, but the problem is that normally they're present with very small quantities. So especially if you only catch the disease at a very early stage, then the concentration is very low. And the detectors that you can detect these come with certain limits of detection. And so if the disease markers are not concentrated enough, then you cannot detect them. And even if the detectors get more and more advanced, if you want to detect the disease as early as possible, you forever need to be able to detect a lower and lower concentrations. So that is a problem. So essentially detecting some of these biomarkers in your body fluids, in blood, in sweats, in your nose swabs, it's like looking for a fish in a very large pond or in the Victoria Harbor. They may be there, but if you just randomly take a scoop of water out, you may not be able to find any fish inside, but it doesn't mean that it's not there. And the lower the concentration you can detect, the sooner or the earlier you can find out whether the person has the disease, and you can start the treatment earlier with a high success of treating the person. So this is a problem that needs solution. And of course, sometimes people are interested in doing research because they want to have some fun. So research is fun because you can think of ways to do different things. So you can have the same target, you can try different methods. We talked about using test tube, microwells, and because we can use droplets, can we detect these diseases drop by drop? And to me, that's a lot of fun if we can do that, starting out from a new concept. And if you want to have successful innovation, you need certain degree of rigor, you need the techniques to be workable, you have a concept, you need to implement the concept as well. So in order, for example, to use droplets to do these kinds of the disease diagnostics or screening, you need to be able to generate the droplets. So here is an example. If we can have a device, this is a microfluidic device, the sample is flowing from the left to the right, forming very uniform droplets at 2100 hertz, so 2100 droplets per second. And if you want to do assay, you need to put in certain solutions to see whether you can detect the sample. So you have to inject the reagents into the droplets. You can do that. Physics and fluid dynamics teach us how to do that. And when you're measuring the concentrations, typically you want to get a value, and the value is concentration. But when you're using droplet, you're using a completely different approach. If you have the disease markers in the droplet, you can make it fluoresce, for example, and in a microfluidic device like this one, if you see a fluorescent droplet indicating the presence of the biomarker, you can put it to the top, indicated by the number 1, and if it doesn't have it, then it's, you put it to the bottom to the waste channel, and you note that by 0. So it's turning the concentration into zeros and ones. So in a sense, this is like digitization. You can think of if you have a solution with a very low concentration, because the concentration is very low, so if you use any kind of detector to try to detect certain compound inside, the noise will be much larger than the signal, so you will not get any signal. But if you break the whole solutions into tens of millions or even billions of droplets, then you're essentially concentrating the molecules in the volume of the droplet by tens of millions or billions times. So concentration is much higher. So instead of getting a single value of concentrations, you get lots of zero, but some ones. So this is the concept of digitizing. And digitizing or digitization can qualitatively change how detection can be measured and can be done. And so here is an example. On the left-hand side, for example, you have a few fluorescent droplets. If you imagine mixing all of these droplets, merging them together, the color will be too light to be seen. You will just see a black solution. But if you break them into droplets, some droplets will be fluorescent, some droplets will be not. And by combining with some techniques to sort out droplets, for example, containing the fluorescent cells inside, you can get really high concentration of droplets, each with one cell. And this is behind some of the technologies that we try to develop in our lab. And we try to use the concept of digitization to benefit or to come up with new healthcare-related technologies. And this is also part of what my InnoHK Center here in Science Park, the Advanced Biomedical Instrumentation Center, is set up to work on. So with our colleagues, we hope to come up with new technologies based on these discovery-driven techniques to come up with new technologies that can be translated and commercialized through instrumentations and devices. So thank you very much for your time.
Thank you very much, Professor Shum. I like your idea of using this, example to exemplify and explain to our young, scholars or researchers on how this whole process can be done. Thank you very much. Well, we actually received a number of questions from our online audience, but since we do not have a lot of the time, so I may have to ask our speakers to really address to maybe 2 of them. So, the first question that we have got here, one of the online audience asked, as a young researcher, how to compete with the world-leading scientists in the field that you're engaged in? May we have 2, young scholars here to maybe share your views with us, with this online audience. How about we have Professor Law?
It is very important to choose the right supervisor. This is I think lots of young people may not know. I mean, if you do a PhD degree, choosing the right supervisor is the most important step of your academic career. There's no doubt about that.
Very practical tips.
So if you have a good supervisor, the supervisor can quickly bring you to your supervisor's level, because you spend 5-6 years with your supervisor basically every day. If you're smart enough, if you're hardworking, and you will reach at least to a certain level of your supervisor. So if your supervisor is a world-class scholar, you will be a world-class scholar. So, and yeah, if you have the wrong supervisor, I'm sorry, so you better do something else.
Well, a good supervisor will give you the right guidance and support. Well, thank you so much. Well, a lot of people love your answers. Well, how about Dr. Chan? What do you think?
So I think for me it's like about like your passion and also your strength and interest. So if you can find those like the junction between your interest and your strength, definitely you can do well. Because in research, basically you will come a lot of like up and downs. So if you don't have the passion, you cannot like keep it going on. So I think this is like how also like we talk about perseverance, right? So in research, we definitely need this element. So I think, yeah, young generation can think about like, what are your strengths and then what are your interests.
Okay, passion can keep us going, right? Thank you very much, Dr. Chan. Well, so the next question, this is pretty interesting. Well, so this audience just shared with us that my parents allowed me to have a happy childhood, and they allow him to, you know, explore different interests like playing musical instruments and like playing basketballs. But later on, after he went to high school, they wanted him to become a lawyer, a doctor, or an accountant. So they like pretty much have a plan for him. So he was asking, if you were me, how would you and what would you do to convince my parents to let me pursue my own interests and become a scientist? Actually, it's a promising future scientist maybe in the future. What are your tips for this, you know, youngster? Dr. Ma?
Thank you. And I think that's exactly why we need more education, not just to our younger generation, but also to the parents,
Right.
to let them know that, you know, the future of INT is here in Hong Kong, and it's very promising. I mean, I think for the student, I think maybe. I think it really, you have to talk to the parents, right? To let them, to express to them really your passion and to show to them your interests. And I think if you're able to, I think, you know, parents will see that. And I think all parents want is for their child to be happy, right? So I think if you're able to show them that, you know, if you, engage yourself and then throw yourself into internships and, you know, and they can see that, you know, you're really interested in this topic, I think, you know, he'll have a good chance. He or she will have a good chance, yeah.
Yeah, just be brave and be honest and share with your parents about your passion. Thank you, Dr. Ma. How about Professor Sham? What do you think?
Yeah, I'd like to share maybe something that I like to normally talk to the students when they're trying to select majors when they're after their year one. I always tell them that think about what you're interested in. Because if you're interested in something, you may be willing to spend more time on it. You may be compromising your time to go out with your girlfriend, to watch movies, or to watch World Cup or other things, but instead maybe you work in the lab. And every year, you don't have to do a lot extra. If you're willing to work overtime, 1%, then if you compound that by 5 years, 10 years, 20 years, the outcome will be tremendous. You will see a really huge difference comparing with your peers. And so if you pick something that your parents want you to do, but your passion is really something else, then you will not be able to spend that extra time willingly to do something that you otherwise would not be doing. And